Welcome to this complete video course on probability. Whether you are a total beginner or looking for a refresher, this video covers everything from the basics to solving complex, real-world problems. By the end, you will be able to measure chance, calculate exact probabilities, estimate them from data, and combine multiple events. Let's get started. Here is what you will master. First, measuring chance on a scale from 0 to 1. Second, calculating theoretical probabilities by counting outcomes. Third, estimating probabilities using real-world data. And finally, combining independent events using multiplication. We will build these 4 skills step by step. This is our roadmap for the journey. We have 4 parts, each featuring worked examples and practice exercises. We start with the language of chance, move into theory, learn how to experiment with data, and wrap up with combining independent events. Keep a pen and paper handy so you can pause and try the problems yourself. Part 1 is all about the language of chance. Before we dive into calculations, we must master the probability scale, learn our standard notation, and understand the power of complementary events. These are the tools you will need for every section that follows. Probability is built on 2 anchors, 0 and 1. Impossible events, like a person living for 1,000 years, have a probability of 0. Certain events, like tomorrow following today, have a probability of 1. Everything else sits somewhere between these 2 extremes. To talk about chance, we use the letter P. We write the event in parentheses and read it as the probability that. The result is always a number between 0 and 1. It is a simple, tidy piece of mathematical shorthand that replaces entire sentences. Most real-life events sit between our 2 anchors. Unlikely events, like it snowing all summer, are close to 0. An even chance, like a coin flip, is 0.5. Very likely events are close to 1. The closer you are to 1, the more certain the event is. This is the complete probability scale. It is a map for every event you will ever analyze. From absolute impossibility at 0, through the midpoint of 50-50, up to total certainty at 1. Keeping this visual representation in mind will help you verify your results throughout the course. Here's the golden rule. Every probability must be between 0 and 1, no exceptions. If you ever calculate a negative number or a value larger than 1, you know there is a mistake in your math. It is a perfect way to perform a quick sanity check. Complementary events are a powerful concept. They happen when a scenario is split into 2 outcomes. One must happen, and if it does, the other cannot. Light bulbs either work or they do not. This binary logic is the foundation for our next shortcut. Because complementary events cover every possibility, their probabilities must add up to 1. This gives us a great shortcut. The probability of an event not happening is simply 1 minus the probability that it does. If a bulb works with a probability of 0.9, then the probability of failure is 0.1. We have finished part 1. You now know the 0 to 1 scale, the P notation, and how complementary events always sum to 1. You have the basic language down. Now let's move on to part 2, where we will turn this language into exact mathematical calculations. Part 2 focuses on theoretical probability. We are moving from simple descriptions to exact numbers. We will explore how to count outcomes using a sample space and apply a simple formula to solve problems involving dice, coins, and cards. Let's dive in. The secret to theoretical probability is equally likely outcomes. When you roll a fair die, every face has the same chance of landing face up, 1 in 6. When every outcome has the same chance, probability becomes a straightforward counting problem. We just count what we want and divide by the total possibilities. This is our master formula for part 2. The probability of an event equals the number of ways that event can occur, divided by the total number of possible outcomes. Remember, this only works if all outcomes are equally likely. If they aren't, we need a different approach. First calculation. What's the probability of rolling a 5? Look at the 6 faces. Only 1, the 5 itself, counts as success. So the probability is 1 divided by 6, or about 0.167. Notice where that lands on our scale. Closer to 0, so a 5 is unlikely on any single roll, but never impossible. Now the probability of scoring more than 4? Here, an event can happen in more than one way. Both a 5 and a 6 count as winning outcomes. With 2 winning faces out of 6 total, the probability is 2 out of 6, which simplifies to 1/3. The recipe remains. Count the winners, then divide by the total. One more with the die. The probability of an even score. The even faces are 2, 4, and 6. That's 3 ways the event can occur out of 6 equally likely faces. 3 over 6 simplifies to 1/2. It makes sense, as half the faces are even and half are odd. The die is perfectly balanced. Let's switch to coins. A fair coin has just 2 equally likely outcomes, heads or tails. Our chosen event, landing heads, is one of those 2 possibilities. 1 divided by 2, the probability is 1/2. It is the same counting logic as the die, just with a smaller sample space. This brings us back to complementary events. The probability of heads is 1/2 and tails is also 1/2. Together they sum to 1. This isn't just an observation, it is a law. Whenever you calculate probabilities for complementary events, they must always add up to 1. This is a perfect way to check your work. When tossing 2 coins, we must list the sample space carefully. Write H for heads and T for tails. Both heads, heads, tails, tails heads, and both tails. There are 4 outcomes, and each is equally likely. Remember, heads, tails, and tails heads are distinct. Always list your sample space before calculating to avoid missing an outcome. With our sample space of 4 outcomes, we can easily find the probability of getting 2 tails. Only one of those 4 outcomes matches. One winning outcome out of 4 total gives us a probability of 1/4. This method works for any situation where outcomes are equally likely. Time for you to practice. Pause the video and try these 3 problems. Remember, count the winning outcomes and divide by the total. Once you have your answers, play the video to see how you did. Let's check your results. For the cards, 48 out of 52 are not aces, simplifying to 12/13. For the socks, there are 20 total, so black is 3/10, and red or blue is 7/10. Finally, the bad apple probability is 1/30. Well done if you got these right. Here is our recap for part 2. The theoretical formula relies on equally likely outcomes. Remember to count all ways an event can occur, and always list the sample space for multi-step experiments. You are now ready to tackle situations where outcomes aren't so simple. Let's head into part 3. Welcome to part 3, experimental probability. Sometimes we cannot use theory because outcomes are not equally likely. In the real world, machines have biases and objects aren't perfect. When we can't count our way to a solution, we measure our way there by running experiments and gathering data. If a coin is biased, the theoretical model fails. We can't assume a 50-50 split. Instead, we toss it many times and record the results. If 100 tosses result in 65 tails, our experimental probability for tails becomes 0.65. Data exposes the truth that symmetry cannot predict. The experimental formula is simple. Divide the number of successful outcomes by the total number of trials. The most important rule here is that this estimation is only reliable with a large number of trials. A few tosses can be misleading, but hundreds or thousands of trials reveal the true nature of the event. Let's look at a case file. A die is thrown 1,000 times, and a 6 appears 200 times. Based on this evidence, the probability of rolling a 6 is 200 divided by 1,000, which is 0.2. Now, we must ask if this is normal or if something is wrong with the die. A fair die would result in a probability of about 0.167 for a 6. Our experimental result of 0.2 is clearly higher. This gap across 1,000 throws confirms the die is biased. Theory gives us our benchmark, and experiment provides the evidence. Used together, they reveal the real-world behavior of any system. Experimental probabilities show up constantly in industry. When a factory tracks microwave ovens, they might find an acceptable standard 92% of the time, a figure based on hard data rather than theoretical symmetry. If you need the probability of a unit being not acceptable, use your complement rule. 1 minus 0.92 leaves us with 0.08. Why do we insist on many repetitions? Because small samples often produce misleading results. Tossing a biased coin 10 times might give you a wildly incorrect estimate. However, as you move from 100 to 1,000 and finally 10,000 trials, your experimental probability stabilizes, settling toward the true value. More trials always mean better accuracy. Businesses use experimental probabilities to make predictions. By multiplying the probability by the number of trials, they can plan for outcomes. For a mail service, a delivery probability of 0.96 across 93,500 letters suggests around 89,760 next-day arrivals. Whether it's staffing or inventory, this simple multiplication drives real-world operational planning. Your turn to practice. Pause the video and attempt these 2 tasks. First, estimate the probability of success and failure for a new component tested on 150 washing machines. Second, predict the number of successful roadside rescues if the success rate is 0.87 over 17,300 calls. Use the formulas we just discussed and play when ready. Let's review the answers. For the washing machine component, 143 successes out of 150 gives us 0.953, while 7 failures gives us 0.047. Note how they sum to 1. For the rescue service, 0.87 times 17,300 gives us 15,051 successful rescues. These estimates help us plan, even if actual day-to-day results fluctuate. Welcome to our final module, independent events. So far, we have analyzed one event at a time, but often, problems involve sequences like tossing a coin and a die together, or checking multiple components. When events do not influence one another, we use the elegant multiplication law. Let's finish this course strong. What does independence actually mean? It means the occurrence of one event does not change the chances of the other. Consider throwing a die twice. The second throw has no memory of the first result. The probabilities remain identical. If knowing the first outcome doesn't change your expectation for the second, the events are independent. Here is the multiplication law. If events A and B are independent, the probability of both happening is simply the probability of A times the probability of B. Remember, this law is specifically for independent events. If an event influences the next, you cannot use this multiplication shortcut. Let's apply the law. What is the probability of rolling a 6 and flipping heads? The die and coin are independent. A 6 has a probability of 1/6, and heads has a probability of 1/2. Multiply them together, and you get 1/12, or about 0.083. Demanding both events happens makes the overall outcome rarer. This law chains across any number of independent events. For 3 coin tosses, the probability of 3 heads is 1/2 times 1/2 times 1/2, which is 1/8. Every additional event you require to happen multiplies in another factor, shrinking the total probability. That is why long winning streaks are so mathematically rare. Before you multiply, always test for independence. Draw a card from 2 different decks? Those are independent. Draw 2 cards from the same deck without putting the first one back? Those are dependent because the first card changes the contents of the deck for the second draw. If the first outcome changes the second, do not multiply. Time for your final practice. Pause the video and solve these 2. First, calculate the probability of flipping 8 tails in a row with a fair coin. Second, calculate the probability that 4 randomly selected components all work, given each has a 96% success rate. These require the multiplication law. Good luck. Let's review the answers. For the 8 tails, multiplying 1/2 by itself 8 times gives 1 over 256, or about 0.004. For the 4 components, 0.96 to the power of 4 is approximately 0.849. Even with high-quality parts, chaining them together reduces the system's overall reliability. You have now completed the entire probability toolkit. Here is the master summary. We have the 0 to 1 scale in complements. We have theoretical probability for equally likely outcomes, and experimental probability for data-driven estimation. Finally, we have the multiplication law for combining independent events. These 4 concepts form the backbone of probability theory. Screenshot this page for your records. Course complete. You have mastered the core pillars of probability. You can now measure events, calculate odds, interpret data, and combine independent scenarios. The best way to keep these skills sharp is to apply them to everyday life. Thank you for watching, and I look forward to seeing you in the next course.